Alright team, welcome to our Introduction to Graph and DFS Search lecture. So before we start, I would like to give very introductory information about why graphs and graph traversal algorithms are super important for the interviews. The reason is they are extremely popular. So if you talk to some assistants, some group 1 teammates, you will see that maybe at least like 30–40% of the questions are coming from graph and graph traversal related areas. So if you ace this area, this means you're going to feel very comfortable if the question comes from those areas. And good news is there is no rocket science involved, meaning all the concepts are easy to understand, but they require your attention. And after some practice, you are going to get the dynamics of how these algorithms work under the hood. Because there will be things like, oh, I have to do this cleanup after this. Oh, I have to care about visiting nodes. Different concepts that at the beginning you might not feel very comfortable with. But in time, with practice, you are going to understand all these tiny details as well. So for this lecture, a few days ago, we did a rehearsal, and it was a lot of fun. Even I learned during that lecture, so I hope it's going to be the same for you guys. And kiddos, the stage is yours. Thank you.
Okay, so we'll start introduction to Graphs and DFS. So I'm glad we've covered trees with lots of time till now, so it will get easier to understand the concept of graphs. So graphs are networks of vertices or nodes connected with edges. So what I want you to focus on is, and these definitions that we're going to see a lot after this, the keywords that are not so familiar. For example, vertices, edges. Knowing these kind of terminologies will help you a lot in explaining your solutions, also looking up in solutions too. So what are vertices? If you remember from the classes from trees, we referred values or classes that represent the values and then the left and right as nodes, right? So vertices are just nodes, node terminologies of a graph. They're just classes that represent the value and then other aspects if needed. And then edges are, if you remember from trees, a parent and the child are connected, right, in some way. So edges are just a way to connect vertices. For example, let's see a simple graph. Let's see a simple graph as a tree. Assuming we have only two vertices, this value and this value are called nodes or vertices, and then the thing that connects them is called an edge. So if they're so similar to trees, what difference do they have from trees? So you can think of graphs as a superset of trees. So they have some differences from trees, but they also include trees. So what kind of difference they have? They can be undirected. What do you mean by that? So from our tree lecture, there's always one path. Like the parent can access the child, but the child can't access the parent, right? But in graphs, it's not always the case. This and this vertex doesn't always have a parent and child relationship. They can have equal value. Two can know that one exists or can access it. One can also know two exist and can access it. Is that clear? Okay. And then the other thing is, there can be more than one way to reach a node. So let's remember from trees. Let's say we have this tree. Which path leads us to 4? There's only one path that leads to 4, right? 1, then 2, then 3, and then 4. The path that passes through the ancestors of 4. There's only one path to get to 4, right? But if it was a graph, there can be more than one way to do that. Like, there could be like this. And then we could have reached to 4 through 5. So there's this. And then there can be cycles. What do you mean by that is, if you start from one node and then go through the graph, you might be able to get back to that node with different paths. For example, we start from 4, go this way, and then go this way, and then you turn to 4. That's it. So there can be cycles in graphs, but in trees, there obviously are not. One more thing, like if they can be undirected, graphs also can be directed. What that means is, it might be the case that the edge only be defined from one vertex to the other vertex, but the vice versa might not work. That means if I have a path from 1 to 2, then it's directed this way, then I can't get back to 1 through this path. Does that make sense? If it's directed. If it's undirected, we can access both, but if it's directed just like trees, it holds that property. So, that's graph. So, if we have the basic concept of what graphs are, let's see how we can represent some. We have two common ways to represent graphs, and then two of them have their own advantages and disadvantages. We'll look into it while discussing them. So the first one is adjacency matrix. I'll use the eraser or keep it. Okay, so we have it. So as the name points, we use a matrix to represent the properties of the graph. How we build this representation is, first, let's say we have n number of vertices or nodes, which means just objects representing, like the A, B, E, D, and C are called vertices, and then these edges, these are called edges. So if we have 5 vertices or n vertices, we're going to build a matrix with size of n by n, which is just like that. And then we'll see what each cell of the matrix represents. So let's use this graph, and then what first we're going to do is find number of nodes. It's 5, so we're going to be 5 by 5 matrix, and then so each cell in the matrix is supposed to represent the relation between this row and this column. So this, let's say, let's pick this cell. This cell is supposed to represent if there is an H between B and C, right? Is that clear? And then let's say this one, let's say this one. This is supposed to represent if there is an H between C and B, between the cell, the relation between the row and the column. So, so what does the zeros and ones mean? The zeros and ones are supposed to represent if there is an H or not. So 1 represents there is an H, and 0 represents there is no H. So I want you to tell me, using those edges for each vertex, for example, let's start with A, what should be the value of each cell? And then, if this represents there is a path, there is a self H. We'll discuss when you get to D. But what should be the value of this? Oh, it's okay. 0, because there is no path from A to A. Or we could just go over the edges and then fill all of the cells representing the edges with 1 and the others with exactly So which cell represents AB? Which cell represents AB?
On the content A and B.
Exactly. So this one, right? And then AC, this one. And then BE. And then BD. And then CD. And then DE. And then DD. So these ones represents the number of edges we have in a graph. 1, 2, 3, 4, 5, 6, 7. 7. So we have 5 vertices and 7 edges. Exactly what we see in the graph, right? So this is one way to represent the graph, and then this is how you build it. You put ones in the cells that represents the edges, and then fill out the rest with zeros. Or you could start with a matrix that starts with zeros at first, and then mark the edges as ones in the next step.
How many eggs have you?
Is it not 7?
I think there was
DA, okay. One here. I missed listing it there, so that's why. Okay. But everything's good, right? Okay. So let's see. Let's analyze this representation through graph operations. So there are some graph operations that are essential, and then we are going to use a lot. One is checking existence of an edge between two vertices. So if I ask you if there is an edge between C and D, what would you do? You just check the cell representing the edge CD, right? Which is this one, right? And then check if it's 0 or 1. If it's 1, there is an edge. If it's 0, there is not. So, one question. What's the time complexity of checking an existence of an edge between B and E? Let's say E and B. Linear, why?
Constant actually, constant time.
Constant, why?
Because you would know the index. So it just it's
So-
just two lists, but it's an index. So you just
Exactly. So since we know the index representing the vertices, it's just accessing one value from a matrix, right? That's why it's constant. And is that clear? The other thing is, the other graph operations that we do is iterating over neighbors of a node. So what neighbors means to a vertex is vertices that are connected with an edge to it. For example, C and B are neighbors to A, and E is a neighbor to B, and D is a neighbor to B. Is that clear? So in order to iterate, as we will see later, we're going to need its neighbors. So we're going to use a lot, like finding the neighbors. So it's an operation that we'll use on graphs a lot. So it's time complexity. I want you to tell me why iterating over neighbors of the node is ON in this representation. Like, the neighbors are, for example, for D, if I ask you what the neighbors are vertices I can get to from D. In this case, you can get from D to A, from D to D, from D to E, right? So A itself, D, and E are its neighbors. Does that make sense? So if I want to know which vertices are neighbors of D, what's the time complexity and why?
Obviously, it's open, so we only have to iterate one row.
Exactly. Since we're only looking at this row and then checking the vertices with one index, it's ON. Is that clear? Okay. So analyzing it, it has these time complexities, like checking its existence is O1, and then finding neighbors is On, and it requires an n-square memory because of the matrix. So it's better for dense graphs, but I don't want to talk about it now. We'll see it after adjacency lists, which is the next representation. So this way of representing is you just store the neighbors of each vertex in a list or some kind of data structure. It represents as if it's a linked list because A just knows the first, like let's say for the A, it just knows that it has an edge connecting to B, and then it has an edge connecting to C, but it's not like we're always using a linked list. We can use just normal lists. So how you build array lists is, let's say we have a way to store all vertices and their neighbors. So let's say for A, B, C, D, and E. For A, we just store vertices which have an edge from A and towards them. So which vertices are there? B and C, right? So for B, D and E. And then C to D, and then D to E, A, and then itself D, and then from E. Alright. So you just go over the edges, and then if you find an edge representing A to B, it means that there's a path from A and then to B. So you just go over the neighbors representing A's neighbors, and then add B to there. And then next time you see AC, it means it's a neighbor. C is a neighbor of A. So you just go to and the array representing neighbors of A, and then add C to there. Is that clear? It's clear, right? It's easy. So what how it's normally represented in a code is, these are usually stored in a dictionary. So these are the keys, and then these are the values. So in order to find neighbors of A, you just check the graph with value A, and then it returns this. Clear? So let's analyze the graph operations that we discussed earlier. How do we check edges between the vertices, and what's its time complexity? Is that it? How do you check if there's an edge between, let's say, B and E?
For node B, I have to iterate through its adjacent elements from its adjacencies.
That means there is a path, right?
Yeah.
So what he said is, you just find the array that represents neighbors of B, and then iterate over it, and then if there is E, that means there's an edge between B and E. If there is no E in that neighbors array, that means there's no edge between B and E, right? What is time complexity?
Like the number of edges between A and B, like N and B, and it's not the whole list.
In the worst case, how many elements can be in this array? All the nodes, right? So it's the time complexity is O(n), right? Okay, we'll go into it. So, iterating over neighbors of a node, that means finding its neighbors. Exactly.
Since we're given a single edge, and we have to look through missing list, so we have to iterate the names of that list. So it will be the order that means.
Since we're representing the trees, so the neighbors in the array, it's exactly the number of the array, right? So it's or n, since the number of vertices could go up to n. Let's return to the thing that I skipped earlier. It says adjacency matrix is better for dense graphs, and adjacency list is efficient for sparse graphs. The reason they say it's like this is, what kind of operations does adjacency list is good at? Let's say. Okay, due to the maybe it's not so random because it's not so obvious. So the thing it's better adjacency list is better at is finding neighbors, because if we go back at the row representing E, if I ask you find the number of neighbors, you're going to over the whole row, right? If I ask you find the neighbors of E this time, you just have an empty list. So it's better in some way if it's not if there is no if the graph is not so full, which means not everything is connected. This is good, because vertices that don't have so many neighbors, you don't have to traverse the whole row to find their neighbors. So adjacency list is better at that. And then adjacency matrix is better at checking if there is an edge between two vertices, right? Because in order to check if there's an edge in adjacency list, you would have to go over the whole neighbors list, but this time it's just checking a cell. So the reason we said adjacency matrix is better for dense graphs is if dense graphs means almost every vertex is interconnected. Is that clear? That means there is an edge. There's almost always an edge between two vertices. So what is going to be the character of this matrix? We're going to see lots of ones and few zeros, right? Since almost everything is interconnected. So if there is an edge between almost every node, we're going to use we're going to see every vertex, like almost every vertex in every neighbors list, right? So since we're going to use the same memory as adjacency matrix for adjacency list, right? If there's an edge between every two vertices, that the adjacency list is also going to take any square memory, and then adjacency matrix memory limit doesn't change. So they're going to require the same memory, but we would have an advantage of checking existence of an edge is O1. So we would go for adjacency matrix since we have that advantage. Okay.
What's the memory complexity of adjacency?
If it's a dense graph, it expands to n squared.
I mean, in terms of number of nodes and
Oh, okay. So a good thing that's brought up here is what would be the time complexity of adjacency list if it's represented as number of vertices and number of edges. We know what vertices and edges are, right? So let's see. What do these values represent? Like, if these neighbors, like each of these lists, each of these lists could be summed up, which value would they give us?
Number of edges.
Exactly, right? Because this is supposed to represent a relationship. this means that there are two edges starting from A and leading to somewhere, and then B represents there's an edge starting from B and then everything like this. So each value in the list represents an edge. So we're going to use a memory for that. So number of edges would be our memory. Yes. So, yes. Yes. Exactly. So if everything is interconnected, if everything nice of you to bring that up. So if everything is interconnected, that means if we have n vertices, how many edges do we have? Like almost n, right? So for every vertex, we're going to have n sized lists. So we're going to use n square memory. Is that clear now? It is, or is it is? Okay. If not, please bring it up now, because it's going to bug you a lot later when we code it and everything. So yeah, think of that. So, and then if we say adjacency list is better for efficient for sparse graph because of if everything is not so connected, or we don't have that many edges that start from one vertex, in order to traverse or find, I should say, its neighbors, we don't have to go through the whole row. We just have to check its neighbors. Like since we have a list representing its neighbors, we just have to go through that, right? Is that clear? Okay. Before going there, there's one thing. If you can optimize this adjacency list representation in order to make it efficient to check existence of an edge between two vertices, how would you change it? Like, in order to find if there is an edge between A and C, you would have to go through a list representing its neighbors, right? You first check if this is C, and then if this is C, and then if it's longer, you just check the whole thing, right? How would you change this representation in order to make checking the existence efficient? If you have any ideas, this is
Changing the neighbors list to a set.
exactly. So if this was a set, in order to check if there is an edge, how would you check that? How would you check if there's an edge between A and C?
I will check the second vertices in the state. And if I try to check it whether there is an edge between A and C, I will find in the set a neighbors set of A.
If there's C, yeah. So what he basically said is, in order to find if there is an edge between A and some vertex B, I just have to check if B exists in that set. So if it exists, that means there is an edge. Otherwise, there isn't, right? So you can make it better this way.
And is there any trade-off for this?
Trade-off with what?
For using a set instead of a list? Is there anything bad about it?
I don't think so. Is it? Is there?
No, it's still
Is there a reason why we choose arrays over sets? Or it's a scenario? I don't know.
any of these operations, I think sets would be.
It depends on the question. There might be a case where it's not so good, yeah. Not so- yeah. But for this case, it's much better. Okay. The other thing I want us to discuss about graphs is not always the question will tell you that it's a graph kind of question, and this is an obvious one, but not everything is represented as nodes. So we want to discuss how grids can be and graphs and represented or discussed as graphs. So first, let's see what a grid is. A grid is and a representation with rows and columns, just like that, since we're familiar with grids. And then let's think of each cell, in this case the intersection between the column lines and the rows lines that are bulleted as nodes, and then neighbors of that nodes are defined in many ways, but let's say we have the exact same grid, and then let's say these are our vertices. Let me name one. So we're just discussing about neighbors of vertices when we have grids. So if it's stated that vertices that exist above, left, right, and below it are its neighbors. In order to find these neighbors, and then A is described as a cell represented with, let's say, I and J. I could be its row number, and J could be its column number. Assuming this grid is a multi-dimensional array, it's not so clear. So these whole vertices, 4 of them, could be one array. We can think of this as a Cartesian coordinate system, but since we normally operate on arrays, let's use the arrays. And then it's a big array containing all of the arrays. Right? Is it clear? Okay. So, what is the I and J value of A? It's on the index 1 row, right? Index 1 array. And then it's on the index 2 column, since we use zeros in the beginning. So, coordinate of A is 1, 2. So, in order to find a neighbor above it, we just decrease 1 from its what? Row number, row index. And then to find its left neighbor, we decrease 1 from its column. And then in order to find the right, we increase 1 from the right, the column. And then in order to find E, we just decrease 1 from its row. So this value is going to be 0 and 2. And then C is going to be 1 and 1. D is going to be nothing. What's D's? Does its row number change? Does it? It doesn't, right? But what value of from row and column change for D relative to A? And then for E, we're picking kind of 2, 2. So that's how we find neighbors in a grid. If it's stated that these values are its neighbors. But it's not always the case that only these 4 values are the neighbors. It can be stated that cells that are in diagonally connected to a vertex can be its neighbors. In this case, these values could be the neighbors too. So, a very good practice that we use to represent neighbors is using direction arrays to manipulate the original vertex. For example, when we use 1 and 2 for A, in order to find B, we just, assuming this is a vector, we just add, for B, we just add -1, 0 to it, and then we get 1 and -1 is 0. So we find B this way. So to represent all the neighbors, we use 0, 1, 1, 0, negative 1, 0, and 0, negative 1. So the other numbers besides 0, which is 1 and negative 1, represent the change in the row, either in the row or the column. So that's how you find, you iterate over this direction vector, and then do changes in the original vertex, and then you find all of your neighbors. Is that clear? So if I say these additional 4 values are its neighbors too, you just add some more vectors into your direction array and then iterate over that. So how many neighbors do we have now? Now that we have added 4, 8, right? So this logic can be upgraded to 3D too, but you can think more about it on your time. Like you are still going to use vectors, but you're not going to use a 2D vector. You're going to use a 3D vector, and your number of neighbors would increase. So think about it a lot, and then if you want to talk about this or anything exciting, talk to me later. So that's it about representing graphs or using grids as graphs. I know some things are not so clear, or not everything is so clear, but if there is any doubts you have, please just raise your hand and then let's talk about it. It's not like I want to do a lecture on the questions, we'll just discuss about it. So, mainly we're going to use two very well known algorithms to traverse a graph. So what do you mean by traversing? So for the scope of this class, let's consider, but let's say traversing is going over the vertices of a graph. Is that clear? Like going over each vertex of the graph using its properties, obviously. So depth first search, let's not be taken by the word search. Let's not say for now we're searching something. We're traversing the graph, going over the graph. So what do depth first search or DFS from now on will do? DFS is exploring as long as you can find an invisible node before backtracking. I know it's not so clear when I first say it, but let's go over an example and then it will be very clear. Let's use this graph. And let's say for now our graph is undirected. So when we're traversing a graph, we choose a starting vertex at the beginning. Let's say for this example, pick A. So first we have to represent the graph in some form, right? So let's pick adjacency list for this. Just like we did earlier, A's neighbors are B, D, and C, and then B's. What are B's neighbors? I want to pick someone. Danny? What's your name? Nati? Okay. What are B's neighbors? A, and E. Exactly. And then, oh, what about E though? It's still there, right? C has A and D as a neighbor, and then D has C, B, and E, and then here.
No, D.
Oh, D has also A. And E has B and D, right? What's different from this adjacency list representation with earlier is E did not has was its neighbors array was empty before, if you remember, right? It's because both of its edges were directed away from it, or directed towards it. So E is a number of E was a number of B and D, but now since it's undirected, both can have a neighbor relationship. So we chose A as a starting point, right? We have A right now. We go as long as we can find an unvisited node before backtracking. But we choose another vertex before from neighbors of A. So let's say we choose the first one, B, right? So now we have let's mark the ones that we have seen. We have seen A because we started from it. Next we chose B. And then we go to B. Let's mark it. So now we choose from these neighbors. And then let's go over these neighbors and find an unvisited one and then choose that one. So these neighbors are A is visited or seen before, and then we see E is not visited before, so we choose E, and then let's mark this, and then let's head to E's neighbors. E's neighbors are B is visited or seen, and then D is not visited, so we choose D, and then we head to these neighbors. Its first one is C, it's not visited, so we choose C, and then let's head to C's neighbors. It's A is visited, D is also visited. So at this point we have exhausted our paths. So we have this graph. In order to revise how we represented the graph, we have a nice way of visualizing this. If we have a graph this way, it can be represented like this in adjacency. What's this representation? Adjacency list, right? And this is how you represent it as adjacency matrix. So the priority of choosing a neighbor in this case is its occurrence in adjacency list. For example, 5, if we chose 5 and we want to find the first unvisited node, it would be 1 because it came early. That's the priority it's taking. So let's see how we're in DFS on it. So first we're going to choose a start vertex. Let's say 4 chooses 6, and then 6 goes for 2 goes for 0, and then 0 chooses 4, but 4 is visited, so it backtracks to 2 also backtracks to 6, and then 6 have another choice, goes to 5 goes to 3 to 1 chooses 5, but 5 is visited, so it picks another 6 is visited, so it backtracks to 3 also backtracks, 5 checks 6, it goes there, backtracks, and 6 has another option, that's 7 if it's not sin. So everything is visited now, not everything is backtracking. It might be a little too fast. So 4 went for 6 went for 2 went for 0, but 0's other option is only 4, but 4 is sin, so 0 backtracks. 2 also backtracks to 6, but 6 has other options besides 2, goes for 5 goes for 3 goes for 1, and currently 1's options are 5, and 5 is sin, and the other is 6 is also sin. Now everything is exhausted, so it backtracks, and then 3 also backtracks. 5 has 6 is seen, so it backtracks. 6 has another option, that's 7, so it goes there. 7 doesn't have any in H, so backtracks. Now everything backtracks to our starting point. So when does our DFS start? At 4. And then when does it end? At 4, because everything backtracks at some point. Is everything clear? Cool. So that's what we mean by explore as long as you can find an invisited node before backtracking.
What if we get stuck? Could there be a case where we can't backtrack anymore?
Oh,
We could backtrack, but we wouldn't have any edges to continue our search.
okay. Oh, another question. Let's start this. Okay. So, I didn't fully understand, but let me rephrase it, and then if it's the same, you're sure. So, let's say we were at F, and then F backtracked to E, and then E doesn't have any other option to go to. Is that the question?
Yes.
But so E was chosen by some node at some point, right?
It was our starting node, and it wasn't chosen by any.
And then that's when our DFS ends.
So we wouldn't search every node. We wouldn't get to every node.
Yes, but we assume that everything is connected at the beginning. So if everything is connected, then we will go through every node in that graph with one DFS. Since everything is connected, you can reach to any node starting from any node.
So this only works if everything is connected.
Yes. If not, like let's say this was not here. So if everything is not connected, then the connected part of our graphs that includes our starting node is going to be visited. What I mean by this is, if we chose F as our starting point for the DFS, then only F is going to be visited. But if we chose any other vertex, then the connected part, I mean by this, is going to be seen or visited.
Yes, but can the connection be directed? Like maybe F is connected to E, but E is not connected to F, like E doesn't know the existence of F. So if we do a DFS starting from A, there's no way we could reach to F.
Yes, correct. That's exactly it. So if there is no H, if it's directed, our graph, if there is no H like this, then that means there is no way to get to F from A or from E. Nice, let's do this.
Is backtracking part of DFS?
Yes.
It says explore as long as you can before backtracking.
What it means by this is go as long as you can, and then you exhaust everything. So if everything's done, then backtrack. So finish everything, then backtrack. Is that clear? So let's assume that everything is or the graph is connected in some way. That means you can reach to any vertex starting from any other vertex. In order to traverse or go over that graph, you would choose one vertex or node and then call the DFX function on it. So let's see what the DFS does, or if it matches with the things we've said. First, it adds itself into a visited state. It's the first line after the function call or statement. Visited dot add node. It marks itself as visited, just like we did. Next, it tries to choose the next node for the next DFS call. That means it traverses over possible neighbors and then checks if one of them is not visited or not seen before, and then let's skip this part, we'll discuss it, and then calls the DFS function on them. Is that clear? So it's exactly what we said, but I used visited.add twice. The thing is, it's up to you when to decide the visited node, but I would advise you to use to add your neighbors before calling the DFS function. That's what I normally use, but it's up to you in how you understand them. It's like marking B when we were at A, and then marking B as visited when we were at A, or marking B as visited when we are at the node. So it's up to you, but you can think of this. This first line does not exist. So let's talk about the rest. So let's see how this code executes with this example. First, we're choosing A. So the function DFS is called with A. And then let's say before calling it, we add A to the visited state. Let's also take a look at our call stack. First it was A, then B was called, then currently we're at E. Then E checks for B. B is visited or in the visited set. D is not. So the DFS function is called with D. So first it adds it into the set and then calls the DFS function. Now we go to D. The first one is C. It's not in the set, so it adds it. It adds it and then calls the DFS function on it. Now we head to C. Then its neighbors are A. A is visited. D is also visited. Checking existence, checking if it's visited is checking the visited state, or if it's in the state, right? So that's how we check if it's visited. D is also visited. So at this point, C's function state ends. The for loop ends. So we don't have any unvisited node to go to. So what do we do at this step? We backtrack, right? Currently we're at C. So C backtracks to D. D stopped at C, right? When it found the first unvisited node, it called DFS on it. It still hasn't processed the remaining 4 loops. So what's the next node? It's B. Checks if it's in the visited node. It is. E. It is. A is also visited. So it has also exhausted all its neighbors. So it backtracks. Oh, yes. So E, the same thing. Checks. Oh, it stopped. It called at B. Now it's at D. Checks D. It's visited. F. It is not, right? So what does it do? Could someone have group? Adds it here. And exactly. Now we head to F. It only has one neighbor and it's visited, so it backtracks. And then at E, we have finished all its neighbors, so it backtracks. And then B was at A and then checks E is visited. It is. D is also visited, so it backtracks. A stopped at B, checks if D is visited. It is. C is also visited. So we started at A and ended at A, so that's DFS. So let's talk about what we talk about after each algorithm that we've discussed till now. Time and space complexity. So I want you to think of what you've been thinking up to this point. Like if I tell you that n is number of nodes or vertices in our graph, and then L is number of edges per node, like number of edges or number of neighbors per node, what would be our time complexity? So this is a popular interview question called float field. It's represented in lots of ways, but this has some backstory on it. So we're given an image and the image is represented as a 2D array of integers, and then the values of these integers could range from 0 to 65,535. So we can have different type of numbers in the array. That's all it says. So we're given a coordinate, just like we talked about earlier. SR and SC could be our analogy to I and J, representing the starting pixel. We have a 2D array. Currently, we know this. It's filled with integers. We know this. Now we have a starting pixel, SR and SC. It could be SR could be its row index, and SC could be its column index, and then our starting index is here. So we have this, and then we are given a new color, one color, any random color, as a parameter. That's 2 in the example, and then we're supposed to perform flood fill on it. So the next thing explains what the flood fill does. So we have a starting pixel, and this pixel is supposed to be representing a vertex or a node. And our, what's this? It's our grid, right? In this grid, our starting pixel is a vertex, and for directionally connected pixels that has the same color as our starting pixel are considered as neighbors. So in the prior slides, we considered neighbors as vertices that are just for directionally connected to it, right? But now it says not only it has to be for directionally connected, it has to have the same color. That means for the given inputs, SR and SC 1, 1. Let's go over that cell. The index 1 array and 1's column. That's this pixel. And as we discussed earlier, the neighbors of this vertex are, if it's for directionally connected, this one, this one, this one, and this one. So those are our neighbors. But this statement has another thing that says, in order to be neighbor, you also have to have the same color. So these two zeros can't be the neighbors because they are not the same color with this pixel. Is it clear? Okay. So we find the neighbors and we change their colors to our new color. What's our new color? It's 2, right? First we change this to 2, then we change our neighbors' colors to 2. So this becomes 2, this becomes 2. There's no other neighbors, and then any other pixel connected for directionally to those pixels also gets colored the same way. Is that clear? So if our grid was bigger, this pixel originally had a color of 1, right? So which elements are its neighbors? These, and this, right? So this process also repeats for this. So this gets also colored as 2, and this is 2, and this is 2. So we do this operation and then return the array after modifying it. So if you see the recurrence relation, it has like a never let's skip the original. This was the original grid, and then we're starting here. This is the imaginary. That's for examples. And never a vertex, which is a neighbor of this. If this is colored, then neighbors of this are also going to be colored, and then there's neighbors also going to be colored with our new color. So if like 8 vertices that are connected to our starting pixel in some way are going to be colored. So in order to see this as a graph example or DFS, we have the starting pixel as the starting point of our DFS call, and then we traverse our graph. In this case, let's not see the zeros as part of our graph. Let's say the colors that are not the same as our starting pixel, because they're not going to be related to the starting pixel in any way. So let's say the graph consists of pixels that have the same color as the starting pixel and are connected to it in some way. So what's the graph here? The graph here is this is connected to this, and this is connected to this, this is connected to this, and this is connected to this, and this is connected to this. Same thing, right? So we can now we see what the neighbors of each pixel represents, and this is our graph. So if we can find a way to find all places of our graph and then change their original values to our new color, that would be our solution, right? So that's when DFS comes in, traversing the graph. Is it clear? Clear, right? So I want you to focus on me implementing the solution. Like, this is a nice way to see how DFS codes throughout the code. So let's find the question we'll need to first. So let me zoom in first. We have the image or the grid as one parameter, SR and SC representing the node of the starting pixel, 1 in the example case, and new color is the color to be changed for throughout the graph. So the elements part of the graph now will have the new color that's passed as a parameter. So as we discussed, we call our DFS function as with a starting point of SRSC, because that's the coordinate of the starting point, right? So let's consider we have our DFS function here, and then we call our DFS function with SR and SC as our starting point. Let's take a look at what type of things we used in a DFS algorithm. First, we used a visited state, right? In order to keep track of nodes that we have seen earlier throughout the algorithm. Next, we're going to need the graph in order to make references and manipulate it, obviously. So, and then find neighbors too. So we have the starting pixel, the graph in a way, and then our visited state. So, what's the first thing that we did looking through DFS? First, it finds its neighbors, right? First, we mark our starting pixel as visited because we're starting from there, and then we have seen it, right? So let's add it to our visited state. Since I can't add two numbers to the visited, let me make a tuple of that starting pixel in order to hash it, and then change its color. This is the first step. Okay. Looking back to what we have done, we have a variable that stores nodes that we have seen until now called visited, and then we added our starting node into our set because we've seen it. I say we've seen it because I moved out the places, but we changed its color, so we've seen it. So we added it to our visited state. Then what we do is we call the DFS function on it. One thing we could keep track is, in order to find its neighbors, not only they have to be connected for directionally, they also have to have the original color, right? So before we change the color, let's keep the original color as color of SRSC, right? So yeah, this is the first step. And then what we want to do is we want to find coordinates that are connected to the starting pixel, or find neighbors of neighbors that are connected to the starting pixel and change their values. So let's head to our DFX function and first find the first neighbors of the first starting pixel. So if you remember what we talked about earlier on grids, in order to find their neighbors, we talked about vectors. So the 4 vectors that could help us in finding these neighbors are, let's call them directions, and their change in column, positive change in column, negative change in column, positive change in row, and negative change in a row. So we want to iterate all over this direction and find all the possible neighbors. So we want to iterate over this, manipulate the original starting pixel, so we have candidate neighbors. So the value of our candidate neighbor is, let's call this new I, and its value is originally SR plus direction 0, and its new J value is SC plus direction 0. Thank you. So currently we have some coordinate, but it's not the case that it's the neighbor. One thing is, this new I and new J could not exist in the image. It means it overflows from the directions. So we have to check that. The other thing the question constraint asked is it also has to have the same color as the beginning pixel. So in order for it to be a neighbor, it has to be in the range of the grid directions. So let's call them n and m, n being number of rows and m being columns. So n is length of image, m is length of the first array, which give us the number of columns. One thing I want you to notice here is, until now on recursive calls, we used global variables to pass constants. N and m doesn't change throughout the function calls. So instead of storing them as global variables, we can just pass them to the DFS function, and then whenever we need them, we can access them right there. So
In this case, we can make them local variables.
yes, but we don't want to redefine them for every DFS call, so we can just pass them as constants. So new I is the x coordinate part of the new possible neighbor. So first it has to be in the range of the grid. So new I should be between it includes 0. It should be between 0 and n. It can't be n because our index ranges from 0 to n minus 1. And our new j has to be between 0 and n. Is that clear? What we just did is check if the possible neighbor is in the grid. So the other thing the question asks us is also check if its color is the same with the original color. So what we can do is we can also pass the original color as an argument to the call, so we can access it here. Oh.
If we are trying to, since we are trying to match it with the original code, and since we are calling a new function since it aligns with our criteria, which is the original code, can't we just check with the existing column? Because we are sure that if it's inside the function, we know for sure that that cell is going to be done.
Oh yes, I see what you mean, but since we're trying to change the color here, we lose what the original color was during the lower steps. So that's what. So it has its values should match with the original color. So image of new I and new j should be original color. So what we can see from here is when I try to access image new I new j, it could overflow, but since we check if new I and new j are in the grid first, since the end part cuts it off if it overflows, we don't have to check when we're trying to access image with new I and new j coordinates. Is that clear? So if it passes this if condition, then we know it's a neighbor because it's for directionally connected to the first node, and its color is the same with the original color. So now we have a neighbor. So when we find the first neighbor that's not on the visited state, well, what do we do? First we check if it's not in the visited, but after checking if it's not in the visited, on the FS, what do we do? We call the FS on it. So let's check if it's in the visited first. So let's say new state is a tuple representing the current coordinate, and then let's check if this coordinate is either in the set. If it's not, we want to call the DFS if it's not in the set. So if it's not invisited, we want to call first we what time. So we add it first into a visited state, and then we call DFS on it. What's SR and this SC on this call? Exactly. And then the other things don't change. Visit changed, but since it's passed by reference and it's a state, we don't have to make sure we keep a copy of it. So that's why we just pass it. So we still didn't do the main functionality of the question. We haven't changed the color of the coming node values. So let's change them here. Image of SR SC should be what? What should be the value of this? Oh, but is it the case that it's always going to be original plus 1? It should be new color from the main function, right? So we have to pass that too. Is that clear? So image of this value, this is going to be new color. Oh, okay, thank you. This is what a DFS code looks like. But first, let's check if finding the neighbors is working. So this code is going to run only for the beginning pixel. So let's see if it finds all the possible neighbors or not by printing the possible neighbors. So new state is after passing this condition is supposed to represent a possible neighbor. So for the first DFS call, let's check if it goes through all of the possible neighbors of SR and SC or SRSC. So the beginning coordinate was 1 1, right? Was it 1 1? So it was 1 1, and then our current possible neighbors are 1 0, right? The one to the left of it, and then the one above it. Just ignore this. We currently SR in the C at the first step was this. So its possible neighbors or neighbors are this and this, right? As it's seen 1 0 and 0 1. So if that's the case, we check if those neighbors are not invisited. We add them and then we call the DFS function, just like we discussed in the lecture. So this DFS function don't have to return anything because we're manipulating the array, the image multidimensional array. So we just have to return the manipulated array from our main function. And we can return it here because since we passed the array as a parameter to our DFS call and then it's manipulated here, it's passed by reference, so if it's manipulated anywhere, the array is going to be manipulated also. So yeah, that's it. So let's test it. Let's give it a try on the first example. So we're printing something? No, we're not, right? So it does the job, but it's not. Let's see how many times this DFS function has been called, or with what coordinate values. First, it's called with 1, 1, because that's our starting pixel. Then it's called with 1, 0, because of the priority we wrote the neighbors vector directions in, because we first chose the neighbor above it, so it chose that one and went for it. And then the next one is 2, 0, and then 0, 0, 0, 1, and 0, 2. It's called 6 times, so it's supposed to change colors of 6 pixels. So we originally had all the 2's that are on the output now as 1's. So all the 2's that exist on the output were originally 1's. So we have 6 2's. So we made 6 from DFS call in total. Let's use the other examples too. It only had one example. Okay. So let's create our own examples. What kind of edge cases would you see on this question? Let's try what if only the starting point was there and everything else was not a neighbor? What would happen? The reason I said this is because most of the time we forget to change or to manipulate or do something with our original starting DFS vertex and then add it to a visited state at the beginning of the main method. But we can move this downwards. We'll see it if necessary, but if we're doing it this way, we shouldn't forget doing this operation. So yeah, it works. Let's check if we have empty things, empty image array, and then we probably won't have SR in this C. Is it the case that the image could be an empty one? Check the constraints. Oh, I'll check it here if I can. So, since the lengths are ranged from 1 up to 50, it can't be empty. But the given starting pixels could vary. So using the previous image, let's change the starting pixel. Let's make this 0, 0. Try to test out your code first a lot before submitting, so that's what we're doing here. We see a 1 that's disconnected from the graph at the end, if you see. That means the DFS call hasn't been able to reach that one because it's not connected in any way from our starting pixel. So let's try making our starting pixel that cell and see if anything changes. And then its value is 2, 2. Then it only changes itself. It doesn't have valid neighbors, so the DFS call wasn't able to expand, so we weren't able to change any colors. Should we go for this? Let's just submit, right? Okay, we're doing this. Oh, what happened?
You did
The wrong code? Oh. Oh, really? Probably. Oh, it worked. So yeah. Any questions though? In order to, we can choose in order not to do this and our main method. So in order not to do this, when we change the new color and adding the visit state, we can make it here srnc and change the color there, and original color is going to be kept. So since this is going to execute for the first starting pixel 2, we won't have to write it up there, so it can be returned inside the DFS call. Let's test this. Oh, and then either, you can choose either of the methods, but whichever comes good to you, I guess. So a good idea brought up here is, might be so confusing, but if it is, it's okay. You can stick to the current implementations we have now, but instead of checking if a neighbor is if a neighbor is visited inside a set, is there a better way, or is there another way to do it without storing it in a visited state or checking its existence, right? To improving the time complexity. Assume that you can change the values of the image in order to store or check if it's visited or not.